In this video, we're going to discuss how the properties of soil and sediment can influence the groundwater flow inside of the earth. Opening on this screen, we have a nice picture of SpongeBob, not only because a lot of people love SpongeBob, but it's going to help us with our understanding of some of our concepts for today. Because just like the ground filled with soil and particles, sponges also have the ability to hold water, and they share a very common characteristic with soil particles to be able to hold water. So to start, we're going to look at the definition and visualization of the term groundwater. Groundwater is a really easy definition to understand because it's the water that is inside the ground. As it rains and the water infiltrates the ground, the water level beneath the surface starts to increase and accumulates more groundwater. Let's take another look at this. I don't want you to confuse groundwater with the term for water table. Water table is the level of water beneath the ground, and below the water table is all of the groundwater that exists. I want us to first take a look at the top of the image where it says unsaturated, and there you have empty pore space. Pore space is the blank space that is between soil particles beneath the ground, and you can see that since it is unsaturated, there's no water between those pore spaces. Below the water table, however, you have saturated soil because those pore spaces are filled with your groundwater. So just to summarize, groundwater is the water that is filled beneath the pore spaces within the soil. So just a little bit more of a visualization of pore space. It's the empty space that exists between soil particles underneath the ground. A lot of times soil particles can be very round in nature, which is very hard to get very tightly packed. So it leaves this empty space between different pieces, but that space is perfect for water to fill. So just to take a little bit of looking at soil container A and soil container B, we want to think about which one of these has more pore space. So I hope you were thinking soil container A has more pore space. There's more empty space between the soil particles when compared to container B. Now there's a measure of how much pore space you have, and that is called porosity. The container with a greater amount of pore space is going to have a greater porosity. It's going to have a greater ability to hold more water. So container A has a higher porosity because it has more pore space, while container B has a lower porosity. It has a lower amount of pore spaces. If you were to try and pour water into each of these containers, container A is going to be able to hold more water because there's more space for the water to go in between the soil particles. So a quick check for understanding, we have 4 different containers, and I'm interested in which one has the smallest porosity. So I'm hoping you're thinking it is container 4. If you look, you have sediments of all different sizes packed very tightly together, which reduces the amount of pore space there, which means it has the smallest porosity. Container 4 would be holding the least amount of water compared to the others. So now we have an interesting question. We have container A and container B. Both containers have the same shaped sediments. They're both spheres. And inside container A, every sediment is the same size. And inside container B, every sediment is the same size. So what we have to do is visualize the pore space in both containers. So we can do that here. The blue shading represents water that fills the spaces between the sediments. This is a really tough question because you really have to think about the amount of pore space as a whole. When you add up all of the pore space in both of these containers, you would actually find that the pore space between them is equal. Their porosity is the same in this instance. So we have to think about how we can put this into words. When you have 2 containers, or even more, that have their own uniform size and also have the same shape, their porosities will be the same. Let's take a look at this again. Container A, every sediment in container A is the same size, and they're all spheres. Container B, also has spheres, and inside container B, the sediments are larger, but they're all the same size within B. A has all same size sediments, B has all same sized sediments, and both containers share the same shape. This will always result in their porosities being equal. So we're going to take a look at this here. We looked at this animation yesterday when we learned about infiltration and runoff, and now we're going to look at it through a different lens when we talk about porosity. So to start, we need to know the scenario. Each container has its own uniform size. One is all small, one is all medium, one is all large. And when you compare each containers, they all have the same shape, they're all spheres. Each container is filled up with water, which means each container has the same amount of pore space. Since you have those criteria, each container contains the same size sediments, and each container has the shape of a sphere. They should have the same amount of pore space. So let's take a look here at the animation. If you remember, the blue between the sediment is representing water. When I start the animation and release the water, we can figure out which container is carrying certain amounts of water. So as the water is released through, what you'll notice is in each of the three containers, they have the same amount of water. They're all holding the same amount, which means the amount of pore space between those sediments was the same. So now I want to give you a different perspective here. Now we're adding a fourth container. So what we have is still the same three containers of small, medium, and large. Each container has a uniform sized sediment. In this last container, they're no longer uniform. You have mixed sizes of spherical sediments. So what we do is when we release the water in this container, we have to see what's going to happen now that we have a mixture in container number 4. What does this do to the pore space? Well, you can see that it reduces it. You do not have as much pore space as you do in the other 3 containers. So let's take a look at this animation. Once we release the water, and the water flows through the container, you can see the first 3 containers, the porosity should still be the same. They should be equal. Now with container 4, when you have those mixed particles, you can see how little water it was holding compared to the other containers. When you have mixed sizes, you're reducing the pore space because those really small sediments can get into the spaces that are left between the larger sediments to close all of those pore spaces, leading to a lower porosity. There's another term that I want to talk about briefly, which is called water retention. To retain means to hold on to something. If you retain knowledge, that means you're remembering, you're holding on to the knowledge, you're remembering what you've learned. So water retention is very similar. It's the ability of soil to hold on to the water as it's flowing through. So if we take a look at this animation, I want you to focus now on water retention. And specifically, I want you to focus on the first container with the red small particles. As the water flows through, it took a lot longer to go through the red small container than it did with the other sediments. That's because water retention is the greatest. You retain the most water when the soil particles are small. Those smaller particles are going to have such smaller spaces individually between each other, which is going to be harder for that water to go through, which allows for more water retention. Finally, the last term I want to talk about is capillarity, and that's the movement of water upwards against gravity due to attraction forces. In this animation, you have one straw on the left that has really narrow walls, and that allows the water to climb up really easily because it has something to attract and to hold on to. This is very similar to what happens in trees and how they get water for the rest of them. So the roots can soak up the water and move that water upwards against gravity because those vessels are really close to each other, which allows the water to grab up and climb upwards. And that's capillary action happening in nature. In regards to groundwater, here we have soil particles that are relatively close together, which allows the water to climb upwards against gravity towards the surface. But what happens when you have gravel, which are larger sediments where you have bigger spaces between them, look at what happens. This water cannot travel upwards. Capillarity is not happening because you have too wide of a space between those sediments. Water can't climb upwards. I want you to think of an example. If you've ever gone rock climbing on a rock wall, if you have all of the rocks that you're trying to grab really far from each other, you're not going to be able to climb up and go upwards because you can't reach the next rock. Same thing happens for water. It can't climb upwards when you have large particles that are really far from each other because there's nothing for the water to grab onto as it's climbing upward. So to have the greatest capillarity, you want the smallest soil particles. I just want to mention one thing for this unit. If you haven't realized already, there's a lot of vocabulary and a lot of notes. I really apologize for that, but there's no way around it. Vocabulary is key for this unit. So whenever you're doing activities or castle learning, please make sure you go back to your notes and make sure you have an understanding of the term that is in the question before you move forward, because vocabulary is everything.